This is 4.4 number 25 homework, and we're looking for a concavity here. We have a interval from 0 to 4 pi, and I think the book might have made a mistake when I looked at CalcChat. They're treating it like it's actually a open interval rather than a closed interval. So 0 and 4 pi are not being treated like they're included. So I need to rewrite f of x. And f of x is equal to sine of 1/2 x. And then find the derivative. So f prime of x is cosine, angle stays the same at 1/2 x, times the derivative of the angle, which is 1/2. And then we're going to find the second derivative. So now f double prime of x. We have a 1/2 going along for the ride. The derivative of cosine is negative sine of 1/2 x times the derivative of the angle, which is 1/2. So we get negative 1/4 sine of 1/2 x. And we want to set that equal to 0 to find where we have possible inflection points. I'm moving up. So I'll multiply both sides by -4 and just not have to worry about that coefficient in front. And then I'm going to have sine 1/2 x equals 0. And I want to know at what angle on the unit circle the sine is 0, and I set the angle that I have equal to those points, those angles. So remember that sine and cosine only achieve the value of 0 on an axis. So we have 1, 0, 0, 1, -1, 0, and 0, -1. And we're going from 0 to 4 pi, and so that's 2 full rotations. So here for sine to be 0, it's going to be at 0 and pi. So we have equal to 0, which we're not really going to use because it's not in the domain, and at pi. And then go around some more, and now we're at 2 pi. And keep going around so you get your 2 rotations and 3 pi. And then we set the angle that we have equal to that. So that's 1/2 x is equal to each of those. And we're going to be excluding more values in just a moment. So now when we solve each of our little mini equations, we multiply both sides by 2. And those are going to give us then our x values. X is equal to 2 pi, and that is in our domain. X is equal to 4 pi, which is not being treated as if it's in our domain. And x is equal to 6 pi, which is certainly out of our domain. So now we have this. And so the only value that we're going to use as a possible inflection point is at 2 pi. So we set up our interval, and here's our 2 pi. And this side will be 2 pi to 4 pi, not including 4 pi. And the other side is 0 to 2 pi, not including 0. And we need test points and test them in the second derivative. So I like to choose values that are on the axes because they're easiest to work with. So I'll use 3 pi on the right interval, and I'll use pi in the left interval. And when I'm saying use them, I mean put them into the second derivative and see what you get. So I'm putting them in right here. I have f double prime of x is equal to -1/4 sine of 1/2 x. And so moving up, f double prime of pi is equal to -1/4 times the sine of 1/2 times pi. And you always simplify the angle first. So that's -1/4 sine of pi over 2, which is -1/4. And if we go to the sine of pi over 2, that's the y coordinate, which is 1. So this is negative. That means for this interval on the left where the test point came from, the second derivative yields negative values, and that means it opens, the function opens downward, it's concave down. If we use our other test point, that's 3 pi, we plug it into the second derivative. And then we simplify the angle. So we're looking at the sine of 3 pi over 2, and that's negative 1/4. And the sine of 3 pi over 2 is the y-coordinate, which is negative 1. So that is positive. And positive in the second derivative for that interval means concave up. The function is opening upward. So we have concave down from 0 to 2 pi. Concave up from 2 pi to 4 pi. And because at the place where the second derivative was 0, we have a change in concavity on either side of it, it is officially an inflection point. So there is an IP inflection point at x equals 2 pi. Why they didn't include those endpoints, I'm not quite sure. There isn't a lot that would have changed either way, though. So, all right. Hope this helped.